Hello, I'm Klara Gregorova, a master student of psychology at Goethe University of Frankfurt. Today, I'm happy to present my recent work showing how neurocognitive computational models can be used to diagnose effective treatments of slow reading. Neurocognitive computational models are ideal for investigating neural processing and behavior. They can detect also relevant sub-processes in, for example, visual word recognition, which is the cognitive process we are focusing on. Here we use the Lexical Categorization Model, the LCM, that assumes a pre-semantic categorization of letter strings into meaningful or meaningless in the left ventral occipital temporal cortex, in the so-called visual word farm area. Our main aim is to test whether we can use parameters relevant for the LCM to predict if individuals will respond to a lexical categorization training. For this purpose, we designed a training paradigm, which was a simple lexical decision task including feedback. Executing lexical decisions is expected to train the categorization process that is assumed to be implemented in the LVOT. We conducted 3 experiments with each 3 sessions of training on subsequent days. Before and after the training procedure, we measured the reading speed. Altogether, we collected data from 75 slow-reading language learners of German. Looking at the pre to post changes, the reading speed increased in all 3 experiments significantly, about 23% on average. Furthermore, the profile of the reaction times consistently resembled the categorization difficulty function assumed by the LCM. These findings confirm for the first time that the lexical categorization process is trainable and that it transfers to the overall reading speed. Still, training benefits show substantial inter-individual variability. This led us to the idea to predict the training outcomes based on the first session data. The prediction process implementing leave one out cross-validation is illustrated in the animation. There were 3 levels of processing. Level 1, feature extraction, which was substantially based on individual random slopes estimated for the reaction times data by the LME4 package, plus some demographic variables. Level 2, feature selection, which should restrict the models to prevent overfitting. And Level 3, fitting procedure realized using multiple regression, support vector machine, and random forest. Altogether, we tested 30 different feature sets and varied also systematically the selection and fitting procedures, intending to find the optimal model. Now I move on to the results. Overall, we had a decent prediction strength with a median correlation of 0.57 between predicted versus observed training outcomes, which is good. Box plots with correlations grouped by the fitting procedure are shown in the figure. The LCM parameter was essential. It was the most often stimulus-specific predictor selected during feature selection at level 2. In the plot, all predictors related to the LCM parameter are highlighted. This finding confirms the relevance of the LCM for the prediction. The best model, which was one of the most straightforward tested variants, achieved a correlation of predicted versus observed of 0.69, with a precision of 86%. Using the model predictions as selection criteria, the reading speed increased by 43%, which was significantly more compared to the unselected group, with an increase of 23%. Finally, we can conclude that the lexical categorization process as the LCM-based computation is central for efficient visual word recognition and reading. These findings implicate that computational models of brain functions are a potent tool motivating new interventions and supporting individualized diagnostics. Thus, neurocognitive computational models open new possibilities for the implementation of highly effective intervention programs. Thanks for your interest. I'm looking forward for the discussion, and also don't hesitate to contact me if you have any questions.